name is Tim. I'm the head of department of philosophy, and I'm really quite happy to be speaking to you all, and also a bit surprised by the turnout, which I wasn't necessarily expecting to be huge, given that my area of philosophy is quite niche. So can I just get a quick show of hands about your backgrounds? And how many of you here are philosophy students? Could you raise your hand? How many of you are maths students? And how many of you are just something else? Wandered in from like the law open day or something, or like, oh well, don't do law because that's invisible. Okay, great. Well, so I'm going to try and give a talk which doesn't assume too much about any of the areas I just mentioned, philosophy or mathematics. But that is basically what I do. I do philosophy at the end of philosophy, which bleeds out into logic, computer science, and maths. And my brief today was that I was meant to talk to you about ways in which mathematics sort of informs and interacts with philosophy. And I think this is meant to be part of a series which will involve various subjects talking to you about for their own subject, how mathematics informs and interacts with the subject. Now, in a lot of cases, that basically comes down to doing applied mathematics. In the canonical case, how does mathematics interact with engineering? Well, you need to do a lot of calculations in order to make sure that various girders don't break when you put them under stress, whatever it might be. And there are plenty of areas of philosophy where there is more of an applied mathematical impact. So, for example, if you're interested in social choice theory or decision theory, that has all sorts of philosophical implications. But speaking just for me, I basically do extremely pure mathematics when I do mathematics at all. It's not because I think that's the only area of maths that's interesting, it's just the only one that I'm any good at, and the only one which really captures my interest. I have before now talked about how Hall's marriage theorem enables us to give a feminist reading of Downton Abbey, which is, in a sense, applied mathematics. But today I'm just going to be talking about pure mathematics. And what I particularly want to talk about is the sort of fruitful interplay between telling stories about mathematical entities and actually getting precise formal mathematical theories out of them. So I'm going to do this via a particular case study, but there are a few others that I could offer. Okay, so just to get things started, what I'm going to do is offer you a very smooth over, somewhat anachronistic history of something, an area known as set theory. And I'm going to tidy it up in ways which I wish it had followed. It didn't quite follow these paths, but things would have been so much more rational in some sense if they had, so I'm going to slow over some of the historical details. So one of the things that you learn very early on if you actually take mathematics seriously is that mathematics is not just about numbers and shapes, it's about all sorts of other things too. But that's something which historically took a bit of a while to understand. The history of mathematics begins primarily with people wanting to count things and then manipulate their countings of things and keep track of how many sheep they have in the field or whatever it is, and then have some form of calculating exchange of these goods, and it's all tied up in the origins of barter moving into actual currency and all of that. But that's all keeping track of numbers. That's one thing that maths is good for. And another thing that maths is very good for is keeping track of shapes, and that's the whole business of geometry. And an awful lot of the history of mathematics is just looking at number systems and geometry. But then something happens largely during the very end of the 18th century and throughout the 19th century, where mathematics becomes more abstract. And it stops doing things like looking at particular number systems and asking about rather more general situations. So a very abstract, very anachronistic example of this is probability theory. Probability theory isn't about a particular system. It's deliberately meant to be about all sorts of different systems. If you learn about how probabilities work, you're learning about how you can calculate the odds when you play poker. You're also learning about calculating the odds in all sorts of other situations. It's not just got poker as its subject matter, but lots of situations which you might describe as random events. So that's an area of mathematics which deliberately is multiply applicable. Now, the more abstract mathematics becomes, the more we want to deal with increasing spheres of generality. And during the course of the 19th century, something becomes particularly salient for people, which is the concept of set. And roughly speaking, a set is just a collection of objects, many thought of as one. And we individuate these collections just by what they have inside them. So we say, For any two sets or collections, you can use those words interchangeably, A and B. If everything in A is in B and vice versa, then A and B are the very same collection. That's what that axiom there says. I've used a tiny bit of symbolism, but if for any x, x is in A, if and only if x is in B, that's how to read that then A equals B. Okay, so this is just an abstract notion of a collection, and some of you may have seen that before. That's the axiom of extensionality for sets. Sets are identical just in case they have the same members. Now, the notion of collection is such a general notion that it finds an awful lot of very general application within mathematics. And during the 19th century, people working informally come up with more and more applications of this idea of set to the rest of mathematics that they're working on. That's all well and good, but if you're working with an informal notion of set, you're going to, at some point, if you're a mathematician, want to tidy it up. And in fact, the crucial question you're going to have to ask yourself is, which sets exist? So just to give a different area of mathematics where we ask that sort of question, if you're working with number systems, at a certain point you'll ask yourself, well, which numbers are there? And you might say there's 0, there's 1, there's 2, there's 3, there's 4, and so on. You might want something more precise than the and so on. You say, okay, for any number, there is a number which is immediately 1 larger than it. You might lay down some various other principles, but this is just by virtue of telling you what numbers there are and how they behave. So that's something people have already been doing, and now we've got this new thing coming along in the 19th century, this theory of sets or collections. We'll want to know which sets there are and how they behave. So that's the question at the top of this slide. Now the naive answer to this is going to be that for any condition you can come up with, I can give you a set whose members are exactly the things answering that condition. So, for example, you might give me the condition sheep in the field, and then I can give you the set of such things. The sheep, all of them, just thought of as a single object going proxy for all of those individual sheep. Or I could give you the set of all French bulldogs currently on Clapham Common. I don't know how many there are, but there is a set of such French bulldogs. And this will lead you to a more general thing, which is for any condition, phi, we have the set whose members are exactly those x such that phi. I've just realised this is definitely not the right version of the slides. Now I'm hoping that this won't cause too much of a problem, but at some point I may need to drop out and bring in other slides. This is my fault, sorry Dan. Clearly something is not updated. Oh well, let's see how far we get before I need to change them. Okay, so the naive answer is this, and you can write that in this handy little way. Mathematicians love notation, and they're right to love notation, because if you choose the right notation, then things become very obvious. This bit of notation is to be read as the set, that's kind of how you use brackets, of all those things x such that, that's how you read the colon, phi holds of x. So that condition holds. Okay, so take any phi you like. It might be that x is a pig, or it might be that x is an even number, or whatever else. Now this naive answer is a lovely answer in all sorts of ways, because it's very clean and precise and clear, and it's clearly the thing that people were working with informally, but unfortunately is catastrophically inconsistent. So it's very easy to see that it's inconsistent when it's presented in this way, but this particular demonstration of inconsistency is due to Bertrand Russell. So if this were correct, that we could come up with a set for any condition phi, then we could choose the set, let's call it R in honor of Russell, the set of all those things x such that x is not a member of itself. And now you ask yourself, is R a member of itself? Well, the condition under which R is a member of itself is just exactly that it is not a member of itself. That's the condition that we laid down. This is the set of exactly those things which are not self-membered. So R is one of those things, just in case it isn't self-membered. It's a member of itself, just in case it isn't a member of itself. And that's canonically a contradiction. That's absolutely catastrophic. Something which holds just in case it doesn't hold. Bad news. So we can't give this naive answer. This is hopefully familiar to a few of you at least. If not, go and read up about Russell's paradox. But I should point out that this is not really a point about sets yet. It's a purely logical point. Russell himself is very clear about this. So you can get exactly the same shape of problem for any kind of relation you like. It's not just about being a member of a set. consider the pug who sniffs exactly those pugs who don't sniff themselves, and ask, does that pug sniff itself? Well, it sniffs itself exactly if it doesn't sniff itself. Contradiction. So we infer, actually, there can't have been such a pug after all. Or consider the man who trolls exactly those men who don't troll themselves. You can troll yourself. Consider that person. Imagine them trying to be like the sort of, I don't know, the troll of righteous virtue, trolling all and only those people who haven't trolled themselves. But there cannot be any such troll because you get exactly the same contradiction. They troll themselves if only they don't troll themselves. So the logical problem here isn't really a point about sets. We just have to live with this fact that we can't have this naive answer. So we need to come up with a different answer. Or we just give up altogether on the whole idea of sets. But giving up altogether on the whole idea of sets would be a bad thing for a number of reasons. First, they're kind of useful. And second, if we just gave up on something the moment we encountered a contradiction, then we would give up on almost all the concepts that we live with. I could give you umpteen other examples, but for now, what we need to do is tell a story about sets which does not lead us into this contradiction. Okay, now being very anachronistic, here is the story that we tell ourselves in response to that paradox. We say, there are certain objects, sets, also known as collections. That bit, so far, so familiar. And sets are identical just in case they have exactly the same members. Again, so far, so familiar. But crucially, and this is a new detail that the naive answer didn't say, sets are arranged in stages. Every set is found at some stage. So we've got this extra notion going on in the background that the naive answer didn't say anything about. This notion of stages. And then we say at any stage S, for any sets that we found before that stage, we find a set at S whose members are exactly those sets. We don't find anything else. Okay, so that's the whole story. And the rough idea is something like this. You're working through the stages, you're sort of clomping along step by step, you're looking down, you've got some things that you found earlier, whatever those things are, you can collect them together and find a set now of those things that were found earlier. That's the general idea here. Now this story seems fundamentally coherent. One of the reasons it seems coherent is that given this story, we shouldn't expect there to be a Russell set. Recall the Russell set is going to be the set of all sets which aren't self-membered. Now that's quantifying over all the sets, absolutely all the sets. But we don't allow ourselves to do that. We say, look, you can only think about the sets that you found earlier to find a set. So you could find the set of all those things found earlier that weren't self-membered. That's okay. But if you try to find a set of all the things that aren't self-membered, you'd have to be standing at a stage outside of all the stages. And you're not allowed to do that. So this blocks Russell's paradox. You don't expect there to be such a set. So that's good. But more generally than that, because of course Russell's paradox is just one paradox, there might have been a ton of other paradoxes lurking around, you really want to convince yourself that you haven't just knocked out one possible problem, but all the problems. The story just sort of seems right, because there's just nothing bad about imagining, okay, now I've got some things, now I squish them together and I have a set of those things. Now I have some more things and I squish them together and I find a set of all those things. It seems viscerally like a story which is okay. Now, at a certain point, there's going to be a skeptic that comes along and says, how can you be sure? And I don't have like an absolute rock-solid answer to that, except to say I think this is as surely coherent as we can really hope for within mathematics as a story. Okay, so this is a nice thing to say about sets, because it's going to avoid the paradox that we had earlier, Russell's paradox. But it's still quite informal, so we now need to make it more precise. We now need to tidy it up so that we can work with it in precise, rigorous mathematics. Okay, things are going okay so far with this slides. Okay, so here's how we can make it a bit more precise. So I'm just going to read off 5 principles from the story that I told earlier. I'm going to use 2 different sorts of variables here. I'm going to use italics to talk about sets and bold fonts to talk about stages, because my story had 2 sorts of entities, sets on the one hand, stages on the other. So italics stand for sets, bold stands for stages. Okay, so the first principle is just that principle of extensionality that I've put up a few times for any sets, because it's italics, A and B. If A and B have exactly the same members, then A is equal to B. As That's just one of the basic principles about sets. We individuate them just by their members. The next principle is a principle about stages. That any stages hold R, S, and T. If R comes before S and S comes before T, then R comes before T. So I'm just introducing a new primitive, a before relation. And it was implicit in my story that I had some notion of before going on with the stages, because I was talking about things you found earlier, and that implies a relation of before holding the stages. And then all this axiom tells you is that the relation of before is a transitive relation. If you're familiar with that terminology. But if you're not familiar with the terminology, anything you might have thought about the notion of before should have obeyed this. If A is before B and B is before C, then A is before C. Kind of a no-brainer, but we'll write it down explicitly. Third principle, for any A, and it's italic, so it's a set, for any set A, there is some stage S, boldface, such that A is, and then I've got a new symbol here, which it's just going to be a new primitive for my theory, but I'm going to read that as A is found at S. Okay, so I'm totally allowed just to come up with any new symbols I like, and here I choose to use just a new one, which LaTeX happened to throw at me and I thought was a good symbol, for reasons I could get into it. I could be bothered. But the basic point is I've got this new symbol, and I'm going to read it as A is found at S. And I certainly need some such notion, because my story, remember, was telling me about sets being found at certain stages. And indeed, this axiom now tells me that for any set, there is some stage such that the set is found at that stage. And that was one of the things I said was crucial about the story. I said sets are found at stages. So this is, again, me just reading off the story. Next principle, a bit more of a mouthful. For any stage S and for any objects A and X, if A is found at stage S and X is a member of A, then there is some stage R which comes before S such that X is found at S. Okay, so, oh, sorry, that should say R, oops, such that X is found at R, my bad. So what this is meant to say intuitively is this. If you've got an object, a set, and you've got a member of that set, then the member must have been found before you found the set itself. And that is something that you can read off the story, because the story tells you you can only form a set when you first got some things that you found earlier, and then you collect them together into a set. So this is just sort of codifying that principle. If you've got a set, then the members of that set must have come earlier. So ignoring the typo, that's what that says. Promise you it's okay. Again, and the final thing is it's our surrogate for the naive comprehension principle that was inconsistent. So this holds for any condition phi that you might think of. And the condition is this. If, I've written it up in a convoluted way, but I'll just explain it a bit more simply. If everything that is phi is found strictly before stage S, then at stage S you find the set of all the phi's. That's basically what that says. If whenever phi holds of X there is some stage R which comes before S such that X is found at that stage, i.e. if whenever phi X is found strictly before stage S, then at stage S you find the set of all the phi's. And again, that's something which is given to you by the story, because I said whenever you're at a stage, given any objects that you found earlier, so in particular the phi's that you found earlier, and you did find them earlier because of this, you'll find the set of all those phi's. Okay, so those are 5 axioms which you can just read off from the story. I've written them out now in a formal way, and if I hadn't put in a typo, they would be perfectly true given the story. That's good because the story is coherent, so we can be convinced that this theory, now which is more formal, is coherent because you just read it off from the story. But we're getting more precise at each stage. Let's call this formal theory ST for stage theory because it talks about stages. This is a very nice theory in all sorts of ways. The main defect of it is that it's got a ton of primitives, it's got boldface and italic fonts, and we wanted a theory of sets, and now I've given you a theory of sets and stages, as if I've got this extra scaffolding that you kind of need to rely on in order to do set theory talk. And if you're a mathematician, you might well think, I don't want to have these extra stages, I just wanted to talk about sets. Well, so here's a fun fact. Yeah, we're definitely getting into the slides that I don't like. Now might be a good moment for me to switch onto the other slides. So, stand by. Okay. I'm back. So, fun fact. Is this something that actually says fun fact? Perfect segue. So that theory that I had earlier, which talked about sets and stages, you can eliminate the talk about stages without losing any information about sets. So it turns out they are an unnecessary thing. But this requires some genuine mathematical ingenuity. What you need to do is to define a certain special kind of set, which we'll call a level. You could have called it anything, but we'll call it a level because it's a bit-like set. A bit-like stage, which does the same job as the stages did, roughly speaking. And then once you've defined this notion of level, you actually only need 3 axioms. They are as follows. First, that familiar axiom of extensionality, that for any sets, if they have exactly the same members, then in fact, you just have one set. Next, the axiom of separation. So for any set A, you can find the set of all those things in A which have F, for any condition F that you like. So if you'd encountered the axiom of separation from Zermelo-Fraenkel set theory before, this is just exactly that axiom. And then finally, an axiom which sort of goes proxy for that idea that sets are all found at stages, which is that for any set A, there is a level S, which sort of does the job of stages. In what sense? A is a subset of S. Is to say, every member of A is a member of S. Okay, the details of this don't really matter so much. What matters is the big picture thing, that you can define this notion of level here in an explicit way which doesn't make any reference to stages. Once you've done that, this 3-axiom theory we'll call level theory, or LT for short. And now the precise statement of that fun fact is as follows. The 2 theories, stage theory and level theory, prove exactly the same formulas which don't use any bold fonts. Bold fonts, remember, were the things that we were using for stages. So this is basically to say they make exactly the same claims about sets. And that's just mathematically provable. Okay, so that's really good because we started out with a story which is coherent, a story about sets being found at stages. We then axiomatized it in a way which was a bit clunky, but all of the axioms were definitely true given the story. And then we came up with a more elegant axiomatization, which gets rid of the talk about stages, just preserving exactly the content about sets, and we haven't lost any information along the way. That's kind of lovely. We've now got this pure set theory, which is totally coherent. Hooray! Now we're not going to run into Russell's paradox, or hopefully any other paradox. I'm sure you're dying to know how to define the notion of level here. So here you go. Here's the magic slide. Here's the trick. I'm just going to leave it there and not say anything about the definition because it's totally opaque if you come at it for the first time. And there's no way I will be able to make it anything other than painfully opaque. All that actually matters now is that it works. Because it is so opaque to stare at, this is why the story I've been telling is anachronistic. Russell's paradox is discovered at the tail end of the 19th century. This precise version of these axioms was first published by me in 2021. It almost ended up being published by Richard Montague and Dana Scott in the 60s. They had a book with a very similar axiomatization. In particular, they defined this operation at the top, the Pilcrow A, the symbol that people in typesetting use for paragraphs. They defined that, and they had an axiomatic set theory all ready to go. They'd written a complete draft book, and it was never published. I can't actually find out exactly why it wasn't published, but I think it's because Montague was brutally murdered, and the 3 authors of the book, Montague, Scott, and Tarski, Scott and Tarski didn't go ahead with publication given the very tragic, horrible murder of Richard Montague. I can't confirm whether that's why the book was never published, but it wasn't, and that's a sad thing. Now, they didn't have exactly this theory. They've defined this operation, and they've come up with a similar theory, but it's, I have to admit, very hard to work with. Then John Derrick and Michael Potter came up with a simpler version of the axioms, and then I looked at that stuff and I came up with a yet simpler version, and this is, I think, probably the simplest way to define the notion of level. So, hooray, now we have a nice story. I just did a little bit of cleaning up at the end. Credit really goes to the four people that formed it. Okay, the main thing is that level theory can explicitly define this notion of set, which is definitely coherent, and it's really good. Okay, so why is it good? Let's give some more fun facts about this theory. Here's a really remarkable fact. Any 2 structures that satisfy the theory that I've just given you must look identical so far as they run, but one might outrun the other. So what do I mean by that? Well, we've got this story which we can continue to use, which is you've got the stages, and at each stage you find all the sets that you can made of things that you found earlier, and you keep doing that. Okay, so one thing that you've obviously left out from that story is how many stages are there? Is there just one stage? You start and then you immediately stop and you don't find anything else? Or do the stages run on forever? You might ask all sorts of questions about the ordering of the stages. And this fun fact tells you that's the only parameter that you've left open here. So, for example, we can tell a version of the story where we say there are exactly 4 stages, and then we'll have told you everything you need to know. We can give you a version of the story where you say there are exactly 150, and then you know exactly everything you need to know. You can give a version of the story where you say the order sequence of the stages is just like the order sequence of the natural numbers that you know and love, and then you've said everything you need to know. Okay, so this is a kind of remarkable fact because the story didn't actually seem like it had pinned down all that much, and yet, incredibly, it pins down everything except the ordered length of the sequences. Indeed, for those who know what an ordinal is, remarkably and provably, the stages are well ordered. That's remarkable because it really doesn't look like it's built into the story. So for those of you who know a bit more mathematics, if you think about the order sequence of the rationals, so the rationals have dense ordering. For all you know at the start of my explaining that story, you might think the stages are ordered like the rational numbers, that between any 2 stages there's an intermediary stage. But we can rule that out. In fact, the stages are provably well ordered, and so our levels are arranged into a nice ordinal sequence. So that's amazing. It turns out that the story is, initially it seems quite sort of open-ended, still only semi-formal, but now we have something which is incredibly concrete. There's just one parameter, and we may just deliberately leave that unpinned down, but if we want to pin it down, we can pin down precisely what this set hierarchy looks like. We can now talk about it as a hierarchy, because we know that any 2 implementations of this story will look identical for so far as they go. The only difference is that one might have more stages coming after the other, but they'll look identical to the first bit. So it turns out our story was very powerful in that way. And now here's the third way in which our story is incredibly powerful. I haven't told you anything about the length of the stages. As I said, you could tell a version of the story where there's literally just one stage and that's it. But if you enrich the story with some quite reasonable claims about how many stages there are, or to put it otherwise, if you enrich your level theory with some not very extravagant claims about how many levels there are, you can embed all of classical mathematics within the resulting theory. So here are the things that you might want to do to enable you to do that. You say there is no last level, or to put it otherwise, for any level, there's a level that comes after it. And you also add there is an infinite level, by which we mean there's a level which has something before it, but it has nothing which comes immediately before it. That's a way of formalizing the idea of an infinite level. If you add those 2 claims to level theory, you can embed all of classical mathematics within this set theory. What do I mean by classical mathematics? I guess I probably mean something like all the mathematics that anyone had thought to do until the early parts of the 20th century. From then on, because people are inventing theories like this, it becomes harder to embed those mathematical theories within this. But, I mean, I don't know exactly which areas of maths you've studied, but I'd be surprised if any of you have studied any mathematics that can't be embedded within this set theory. I'd be interested, but I would also be surprised. Okay, so how do you do this embedding? You do it by finding proxies for your favorite mathematical objects within your set hierarchy. So the basic gist is, your hierarchy is incredibly well structured. You've got this incredibly tightly constrained story, which tells you how all the objects arise from previously found objects. And you've also now enriched your story with claims saying, actually, there's quite a lot of objects. So the net effect is to say, I have a ton of objects, and their fine structure is incredibly tractable. So now, if you come along from some other area of mathematics and say, I want to deal with a system which has such and such properties, I say, look, I've got so many things over here, and I have such tight control over how they behave, that I can give you something which answers to what you wanted. So maybe you say, I want something that looks like the natural numbers. And I say, great, easy. The levels themselves, the first few levels, they'll do as a proxy for the natural numbers, because they're arranged in the sequence of a natural number sequence. Job done. And then you say, no, I want something more than that. I maybe want the real numbers. You say, yeah, no problem, I can do that. I'll just take the power set of what I gave you as the natural numbers. They'll behave like the real numbers. I won't give you any more versions of that just during the talk, but the general gist is you have so much stuff and so much control over it that you can just embed anything from any classical mathematics in this set theory. And that's why it's a super duper powerful theory. So this is kind of nice in various ways because we have this story which is obviously coherent. We have, it turns out that it is then incredibly tight control, and then if we just add some principles about how much stuff there is, then all of classical mathematics can be embedded in that. Okay, this sometimes leads people to say, as a result, we discovered that mathematics was all just set theory. And I don't think we should say that. I'm not going to tell you that we shouldn't, but I don't think we should immediately say it. The first point to make is a fairly obvious point. On the previous slide, I told you that you can embed classical mathematics within set theory. I didn't tell you that you should or that you must. Now, it's arguable that should entails can, must entails can, but can doesn't entail should. In fact, that's a famous line from Jurassic Park, which I discovered. One of my students wrote it in his essay for me. He wrote, in short, they spent so long asking whether they could, they forgot to ask whether they should. And I wrote in the margin for comments, nice Ian Malcolm reference, and he had no idea what I was talking about. Like, does some of you at least know? Okay, there's some ones. I assumed that had become, and for good reason, a cult classic. But anyway, the point there is that can does not entail should, right? You can do all sorts of things that you really oughtn't do. That's a very important point. If that weren't possible, then ethics wouldn't be possible. And this is a case of sort of mathematical ethics. You can embed all of classical mathematics within set theory, but should you? And should you go around telling everyone that that's the right thing to do? Well, no. Pause before you do that. That's an obvious point, I think. A more subtle point, though, and basically the point I'm going to end with, is you can embed all of classical mathematics within set theory, but you can also embed all of classical mathematics within various other theories that are not set theory. So then, just because you can embed it within set theory, well, here's an alternative. So that really emphasizes that maybe it's better to embed it in that other thing. Or maybe this whole idea of embedding is really not to be thought of along that way. So what I'm going to do now is illustrate some of these alternatives to set theory and then shut up and leave you to ask questions. Okay, so here's where things get fiery. Because I told you that this was about telling stories about mathematical objects, and so far I've only given you one story, the story about how sets are found. But now I'm going to give you not just a story, but a template for generating stories, which I call the wand set template. Here's how it works. It's very much like the original story about sets, but when you're forming sets, you also run around with a bunch of magic wands. And at every stage, when you've collected objects together, you just hit absolutely everything you can with a magic wand, as well as collecting sets. So you've just got this extra process of discovering things. Magic wands. Woo. Okay, so it's a template, so I haven't told you anything about the wands yet, just that you have some. And here's a slightly more precise codification of what I just said. So your mathematical objects are found in stages, and for every stage S, the first clause is very much like the thing you found before. Any things that you found before that stage, you find at that stage. The bland set, I emphasize that it's bland because it's boring, because it didn't involve any wands in this, whose members are exactly those things. That was familiar. And then also, for anything A you found earlier, and for any magic wand W, you find the result of whacking that object with a magic wand, provided that that actually gives you something other than a blank set. Okay, so I've enriched the story. You've got magic wands now. But it's still reasonably constructive, because you're still just hitting things with magic wands, so it's good. Okay, template because maybe you don't have any wands. If you have no wands at all, this just collapses back to the original story. The original story is just this, but where you didn't have any wands. If you have one wand, then presumably you're going to find some extra objects. But I will need to tell you about the effects of that wand. And maybe you have as many wands as you have natural numbers. Ooh, all sorts of things might happen. What wands might you have? What might these wands do? I want to leave it open-ended because I want to encourage you all in the spirit of storytelling. And you can tell any story you like, provided, and then the sexy clause, provided that what you say is reasonably constructive. So what do I mean by that? Well, in a moment I'm going to tell you who came up with the phrase, but roughly what I mean is this. When I was telling you the story about sets, I told you that you only needed to pay attention to things that you had found earlier. And that was what prevented Russell's paradox from rearing its ugly head. Because you knew that if you found a set of a bunch of things found earlier, that set might not itself have been found earlier, and so that's what keeps you away from Russell's paradox. The same sort of thought is what I want to appeal to here, that your wands should behave in a way which doesn't involve you sort of looking wildly around all over the place in the sort of sense that would lead to Russell's paradox. I don't have time to explain precisely how I would want to implement that. Just to say, you can, if you think carefully about the story about how you escape Russell's paradox, and you're careful about this, then you can make precise this notion of reasonable constructiveness. But again, this is one of those moments where we move from an informal story and a rough intuitive idea for keeping things coherent to a precise formal theory. One of the formal things we need to do is spell out this. That's hard, and it would be kind of unilluminated for me to say much more than that. This is a challenge, but I think it can be answered. Now, why am I interested in this? Well, partly it's because of this incredible book by John Conway, excellent mathematician. He has a book called On Numbers and Games, which was printed in 1976. And on page 66 of this book, in the appendix to part 0, so the book in two parts, part 0 and part 1, and this comes about halfway through the book, he calls for a mathematician's liberation movement. And part of the tenets of the mathematician's liberation movement are, he says, objects may be created from earlier objects in any reasonably constructive fashion, and equality among the created objects can be any desired equivalence relation. Now, he has a particular reason for calling for this mathematician's liberation partway through a book. He has spent the first half describing a theory of numbers which is sort of built from a theory of games, and his theory of games is precisely a particular version of this. So he has this theory according to which games are built out of previous games, and there is an equivalence relation on those games. I'll say a little bit more about that maybe in question and answers. But I think that it's an excellent idea, and what he's after is a sort of a wonderful exhortation to make pure mathematics a sort of playground of the human intellect. And I think this template that I've offered, the one set template, realizes Conway's idea pretty well. Because this idea about creating objects from earlier objects in any reasonably constructive fashion is just what I was saying about having wands, right? So long as your wands have a reasonably constructive action, then to create an object out of earlier objects in a reasonably constructive fashion is to collect all of those objects together into a set and then hit it with the right kind of wand. So my wands are implementing bit 1, and then equality among the created objects can be any desired equivalence relation. Well, what I'm saying there is I'll need some principles that tell you if you've got one object and you hit it with a wand, you've got another object and you hit it with a wand, do you get the same thing both times? You'll need principles that answer that, and that's going to be the desired equivalence relation. So my one set template is an attempt to realize Conway's liberation movement. And then, and here's the remarkable and exciting fun fact which is exciting enough for me to say it's a theorem, all reasonably constructive ways of fleshing out the template. When I say reasonably constructive, all the caveats from before apply, but I need to make that precise, are synonymous. Okay, so I just need to tell you what that means, and then I'm done with my talk. So, to say that two words are synonymous is to say something like, I don't know, consider the word vixen and the word female fox. Those are synonyms. Or oculist and eye doctor. But we're not dealing with exactly that notion of synonymy, because here we're talking about a relationship between formal theories. The idea here is best thought of in terms of using an automated translation service. So I don't speak any Turkish. If I want to talk to someone who does speak Turkish and they speak no English and we can't find any other common language, one thing I might do is go to Google Translate, type in a sentence in English, and it will output something in Turkish, and I'll hand the Turkish sentence over to the person who speaks Turkish. But I might be worried that I have not got the right translation. And a not perfect test, but a good test for whether you have the right translation is you take the Turkish sentence and you put it back into Google Translate and you translate it back into English. And if you get back where you started, the same English sentence, or a sentence which maybe is slightly different but has essentially the same meaning, it's a good bet that you have the same, you've done a successful translation. It's not fail safe, but it's a good bet. That's basically the idea of a synonymy. So if we've got two theories, S and T, what we want is that we've got translations that take us between the two theories, which I've written as sharp and flat, just because, why not? And they should carry you over such that if you've got a sentence which is a theorem in theory T, and you translate it over into S, well, because it was a theorem on the one side, the translation should be a theorem. That's what it means to have an interpretation. And then to have these interpretations giving you a synonymy is just to say that when you compose the two interpretations, when you run them back to back, you get back where you started. Or to put it more precisely, for any sentence phi in the language of S, S proves the biconditional that phi holds if and only if its double translation holds. And similarly for T. So this is that idea of doing the translation both ways gets you back where you started. Okay, so the result is you've got all of these different theories apparently telling you very different things about mathematical worlds, but they're all synonymous. They are perfectly intertranslatable. Here's a way to think about it, which is maybe instead of the Google Translate one, let's just try a different version. Some of these, hopefully at least one of these sticks. Think about coordinate systems. Most of you have probably used Cartesian coordinates for a two-dimensional system. So you've got an x value and a y value, and that pins down any point in the plane. You'll be familiar with the fact you can also use polar coordinates. So again, it's two pairs of numbers, but now one of them is the distance from the origin and the other one is the angle from the origin. Doesn't matter which of those systems you use, they're essentially just different notation systems for the same underlying stuff, right? And there's a perfect way of translating back and forth between them. Or to take another example, maybe some of you have played around with colour stuff on a computer and you've looked at it in terms of red, green and blue value, but you can also translate that into hue, luminance and saturation. And anything that you can pin down in terms of an RGB value, you can pin down in an HSL value and vice versa. Again, it's just different notation system for the same stuff. Let's take a third example. If any of you have ever worked with logic gates or engineering stuff or bits in computer science, you'll be aware that you could do everything in terms of NAND gates. That's how all computers are built. We could have built everything in terms of NOR gates. It doesn't matter which ones you take as primitive, because you can just translate any claim in terms of NAND into claims using NOR and vice versa. The reason we use NAND gates is because they're better to engineer. It's just a very, very practical reason. Okay, but in all of these cases, we basically have perfect translation back and forth, just a different notation system. And that's another way of thinking about what's going on here. You might even think about that in terms of the Google language example that I gave, where you're translating things back and forth with an automated translation service, saying, okay, we've got English and we've got Turkish, but in some sense, these are just different notation systems for the same underlying things we want to say, using different words for each of them. Well, what I'm telling you now is that any loosely constructed implementation of the one set template is perfectly translatable. So they are, in some sense, just different notation systems for the same thing. But this is bizarre and exciting and gives you a new way of thinking about mathematics, because the one set template gives you all sorts of stories which apparently look very different from one another. So the ordinary story that I told you for the first 35 minutes of this talk, just about sets, that's an instance of the one set template. It's the one where you don't have any ones. But you can also, if you're cunning about how you set this up, make it so instead of thinking about sets, you're thinking about a hierarchy of functions. So the general idea is, you're not talking about sets at all, you're talking about functions, and at every stage you form all possible functions whose domain and range are exhausted by everything that you've found so far. Or you can instead tell a story about a hierarchy of multi-sets. If any of you do computer science, you know you've encountered those. Those are more common in computer science than maths. But whereas a set can only ever have one copy of each object, a multi-set can have any number of copies of an object in it. And you distinguish it in that way. Conway's two-player games also count as an implementation of this. So Conway's theory of two-player games is beautiful, and I have to sketch that and then finish. Here's the idea. Think about a game of chess, right? Hopefully you're all familiar with how that works. Now think about the following slightly different game. It's exactly like chess, except you all start with the white king pawn has been moved forward 2 squares, and the black queen's bishop pawn has been moved forward 2 squares. So you all start as if you have just done the first moves of the Sicilian defense. It's a slight variant of the game of chess. Okay? It's 2 moves in. Think about that a bit more and you realize that when you're playing a game, to make a move in a game is just to move into a different game, a slightly more specific game. Right? So you can think of each move in a game as a series of options for choosing another game from a codified list of such. That's Conway's insight. And the theory of two-player games for Conway is just this. You have options for a player, let's call them left, and for a player, let's call them right. And the options are themselves just games. But what is a game? A game is just a set of options for a left player and a right player. So it's just a pure hierarchy of two-sided games. Or you can just think about this now as two-sided collections, because the idea of them being left and right is immaterial. It's beautiful, and Conway uses this theory of games to do all sorts of amazing stuff. Such a beautiful idea. It's, in some profound sense, not the theory of sets, because these things are two-sided, whereas sets don't have multiple sides to them. But, via the theorem that I gave you earlier, Conway's two-player game stuff is synonymous with the theory of sets. And various other things as well, which I won't go into. So the basic gist is, it turns out that any reasonably constructive way of approaching mathematics, this is now getting very hand-wavy, just comes to the same thing at bottom. It just comes to this stuff that you can get at using collections of things and things you can hit with wands. And in fact, you don't ever need the wands if you don't want. That's not to say that mathematics is just about sets. It's just to say that there is this extraordinary core of what you might call as loosely constructive mathematics that you can dress up in all sorts of different clothing, in much the same way as you can dress up points in the plane with Cartesian coordinates, or you can dress them up using polar coordinates. And maybe it's more useful to dress them one way rather than another, because some calculations are easier to do using Cartesian coordinates than polar coordinates and vice versa. But fundamentally, you're getting at the same mathematical content, however you dress it. So that, yeah, that's something I have been interested in, this sort of ability to stare at maths, tell a bunch of stories, make them more and more precise, make them precise in apparently very different ways, and then it turned out that you're always getting to a single robust core in the end, the core that is got out by this synonym result. Yeah, I'll stop there. Thank you.